Welcome everyone. So this is one of the modules of the TYC course, and I guess if you've been in that course, you've seen all sorts of cool stuff. And so this is now a module focused on understanding electronic excitations, Green's functions, and sort of all of that stuff that, if you're sort of familiar with DFT, you maybe hear about, but maybe you're not quite sure how it actually ties together. And so what I'm trying to do is basically explain how this sort of the connections between the sort of basic materials modeling techniques like density functional theory, experiment like photoemission spectroscopy, and these beyond DFT methods like GW. So that would be the goal. I am Johannes Lischner, and I'm a reader in theory and simulation of materials at Imperial College. That's my email if you have any questions. And so the module will be this week and next week. And so this week we'll start sort of more with a less rigorous and more hand-wavy introduction to GW. And then once we sort of understand, this motivation a little bit, then we'll try to go to the basics and trying to see if we can derive this method from sort of a first principles starting point. Then we'll basically introduce this concept of a Green's function and why that's a useful thing to look at. And then next week, we'll look at how to use Feynman diagrams to calculate a Green's function. And basically, I'll tell you a little bit how practical GW calculations work. So if you want to calculate, let's say, the band gap of a material, then there are certain computer codes, like you might have heard about Berkeley GW or the Yambo code, or and basically I'll talk a little bit about the considerations that go into these practical calculations. Now, do feel free to interrupt me at any time. I mean, the more we discuss, the better. I'm very happy to, cover less material in favor of having more discussions. Anyway, so let's get started and start with the question, why do we need these methods, or why should we? Why is there a need to go beyond density functional theory, which is, as you probably all appreciate, an extremely successful theory for calculating the properties of materials. And because we have Karin in the audience, we'll use as an example photoemission spectroscopy. So how does that work? So let's say we have a block of material. So that's our sample. Let's say could be anything. Let's say it's a little piece of silicon. And what we'll do is we'll shoot a photon with energy h bar omega at the sample. And then, so we assume that the sample, so this is our material. We'll assume that initially it contains n electrons and is in its ground state, which we'll denote by n0. So that's, the piece of silicon has n electrons, n presumably is a very large number, billions. And for simplicity, we'll assume that, it's in its ground state. And that what happens is, of course, if this photon has more energy than the work function of the material, by the photoelectric effect, we can knock out an electron from the material. And if we put a detector somewhere here, we can measure, for example, the kinetic energy of that electron. And of course, what we can say is that what we have now, instead of a material with n electrons, we have a material with n-1 electrons, because one's at the detector, or equivalently, we can say that we have a material with a hole, right? Okay, so that is basically how this experiment works in a very simplistic way. How can we now learn from the things that we can control or measure something about the material itself, right? Which is why we do photoemission spectroscopy. We want to learn something about the properties and the electronic structure of the material that we're probing. So let's see. So the idea is that we'll use energy conservation. And so what that means is that the energy before the photon interacts with the material must be the same as the energy of everything after it has interacted with the material. Now, initially we have the energy of the photon and the energy of the material, which is basically the energy of n electrons in their ground state. We'll denote that by En0. And at the end, we have the photoelectron with the kinetic energy k squared over 2m, right? And we have the energy of the n-1 electrons that remain in the material. And now there's a little bit of a subtlety, because these electrons don't need to be in their ground state. They could also be in an excited state. So what we'll put in here is a little lambda, which will label one of the states of the material. Could be the ground state, or could be an excited state. So that is basically what energy conservation tells us. Now we can rearrange this equation a little bit, so we can put everything that we know or control onto the left-hand side. So of course we can control the energy of the photon, and we can measure the kinetic energy of the photoelectron, right? But the things that we typically don't know are the energy of the ground state. And of course, we also don't know the energy of the n-1 electron systems in their excited state, right? So the left-hand side we know, the right-hand side we don't know. And so what one typically does is one calls this energy difference, we'll define by epsilon lambda, and we'll call that a so-called quasiparticle energy. So that is defined as this energy difference on the right-hand side. And basically by changing the photon frequencies, we can map out the different quasi-particle energies that the material can have. And this allows us to reconstruct the band structure, or to measure the band structure of a material. Let me show you an example. So here, somebody has done a photoemission spectroscopy experiment on diamond, and well, you can sort of very nicely see this band structure that you can measure from these considerations. All right, but of course, photoemission spectroscopy is just one technique that probes these so-called quasi-particle energies. There are many other techniques that probe similar quantities. There's something called inverse photoemission, where you actually shoot an electron at the material and measure the light that comes out. There are things like scanning tunneling spectroscopy, where you have some surface and you have a tip, and basically an electron can either hop from the tip onto the surface, or you can have the reverse process where an electron tunnels from the surface to the tip, and again you leave a hole behind. And then there are transport measurements. For example, you could have sort of a molecule or some sort of nanoparticle between two contacts, and if you apply a voltage, an electron might hop onto your molecule or whatever and then move to the other contact, right? And all of these experimental techniques probe essentially these quasi-particle energies, because in these experiments the number of electrons or holes changes by precisely one. Right, so there's a lot of these spectroscopic techniques that are extremely useful for understanding material properties, and what they all have in common is that they measure these so-called quasi-particle energies. So they are very important, and what we want to do is, of course, understand how we can calculate these quasi-particle properties. So let us now next ask the question, how can we model, let's say, a photoemission experiment? And based on what you have learned already, it would be quite natural if you said, okay, I'm going to do a DFT calculations, I'm going to use VASP or quantum espresso, whatever your favorite code is, and calculate the band structure of the material with density functional theory. All right, so what does that mean? Well, in practice, what it means is that we would have to solve these so-called cone-sham equations that you're probably familiar with. They look a lot like the Schrödinger equation. So you've got a kinetic energy. You've got basically the interaction of the electrons with the ions or the atomic nuclei. Then you've got the Hartree term, which basically describes the electrostatic repulsion of the electron with the electronic charge density. And then there's, of course, this exchange correlation term, which is complicated and we have to approximate somehow. So that is the cone-sham equation. And when we solve it, we get these cone-sham energies and cone-sham wave functions. And basically, if you make a plot of these cone-sham energies as function of the crystal momentum, you can basically make a graph of a band structure. Now, we know that, as I said before, DFT is an extremely useful theory. You can calculate a lot of different things with it. But sometimes it's important to remember the fundamentals of density functional theory. And the fundamentals of density functional theory, the basic theorem is, of course, the Holmberg-Kohn theorem. And we should remind ourselves what that actually tells us. And it tells us that the fundamental things that we can calculate with DFT is the total energy of the ground state, where the emphasis is here on the word ground state, and its electron density. Right, so those are calculated. Those are the basic quantities that we calculate in DFT. Now, you already should be quite suspicious now, because DFT gives ground state properties, but when you go back to what I've just told you about photoemission spectroscopy, I've told you that photoemission spectroscopy involves excited state energies of the n-1 electron system. And so that is clearly something that, you know, DFT does not, by its nature, actually produce. So there is a little bit of a problem. And but there's more problems, because, you know, if you follow sort of this this procedure that I've just outlined, what you would do is you would compare basically these cone-sham energies to the experimentally measured quasi-particle energies. Now that should also ring some alarm bells, because if you go back to the other fundamental part of DFT, and that is basically the cone-sham approach, you will remember that these cone-sham electrons, whose wave functions are the cone-sham wave functions, these electrons aren't the real electrons, right? They are a fictitious set of electrons that are just very convenient objects mathematically, but they actually do not really have any physical reality. So they're different from the true electrons that we remove and add to a material. So it's important to remember that these cone-sham energies and wave functions are not physically meaningful, and I guess I shouldn't miss the most important word, are not physically meaningful quantities. Right? If you remember, Kohn and Sham introduced these electrons because it was just so damn hard to approximate the total energy as function of the density. So that's the reason why they introduced these Kohn-Sham electrons. But you know, it's very important that the Kohn-Sham energies and wave functions are you know, not physically meaningful quantities. So there is an important exception to this rule, and that is that in exact DFT, the Kohn-Sham energy of the highest occupied molecular orbital is actually minus the ionization potential, and that is known as Janus theorem. So if you had the exact exchange correlation potential, then the HOMO energy, the HOMO Kohn-Sham energy, would actually match with the experimentally measured ionization potential. But as you know, of course, in practice, we never do have these, we never have the exact exchange correlation functional. So in principle, of course, there's a problem, but in practice, very often there is not. So a lot of people actually do compare these Kohn-Sham energies to the measured quasi-particle energies, and quite often you get a pretty good match like here. So again, on the left is the photoemission spectrum of diamond, and on the right is a DFT band structure. Now, actually, they've cheated a little bit in this paper. They have actually stretched this DFT band structure. So they've rescaled the y-axis to make the agreement better. So there is a little bit of cheating involved in this result. But you see, at least qualitatively, you know, it often makes sense to compare these DFT band structures with experimentally measured quasi-particle energies. So but you know, in practice, it tends to work out this way, but you know, there's no guarantee that it always will work out that way. So in practice, we often find that the DFT cone-sham band structure of the occupied bands agrees at least qualitatively with experiment. So in photoemission, of course, we only measure properties of occupied bands, and if we only plot the cone-sham band structure of these occupied bands, it tends to agree. But one of the properties where that often don't come out so well are band gaps. So let's take a look. So here you see the band gaps of something like 20 or 25 different semiconductors or insulators. On the x-axis is experiment, on the y-axis theory, and the blue dots are the cone-sham energy gaps obtained from density functional theory with the local density approximation. Perfect agreement between theory and experiment would mean that the blue dots would have to lie on this green diagonal, but clearly they don't. You know, you see for materials with large band gaps on the right-hand side, you know, the LDA gaps are often, you know, underestimate the true gaps by several electron volts. And sometimes when you look at materials with very small band gaps, DFT actually predicts a negative gap, or so it actually gives you a qualitatively different result and predicts the material to be a metal when in fact it's a small gap semiconductor. So there is a problem, and of course the reason why we're interested in band gaps is, for example, when we're studying optical properties of materials. So let's say you want to study a material for a new type of solar cell, then the band gap tells you sort of the energy at which the material can absorb photons, which of course is important for a solar cell. And so you need to, so that's why, for example, these band gaps are very important. And we would like to calculate them accurately, but DFT, at least with these simple approximations to the exchange correlation energy, tend to fail. So there was a question from Hanbo: why do they need to stretch it? How is it underestimating the band gap? So I guess that's a question about this photoemission, about this band structure. So, I mean, they need to stretch it because the width of these bands, so basically the bandwidth is sort of this different. Again, that's something that's underestimated by a couple of electron volts in DFT. And so, so DFT again fails for if you want to get a quantitatively accurate value for the band gap, and you know, to make the agreement look nice between theory and experiment, they stretch the band structure empirically. And let's see. Okay. So
I have another question.
Yeah, go ahead.
About that spaghetti plot you just showed, the band structure. I'm wondering, why does the Kohn-Sham sort of orbital gives this even the qualitatively similar plot to the experiment? Because you just said Kohn-Sham orbitals are virtual orbitals. They're basically just figments of imaginations. And how come these two plots are sort of identical in terms of shape, of course? So,
yeah, I mean, a priori, you should be surprised. So if you know, if you didn't know anything else, then this would come as a surprise, right? Yeah. Now, I guess in practice, we know quite a lot of things. So we know, for example, that Hartree-Fock, there's a so-called Koopman's theorem in Hartree-Fock. So in Hartree-Fock, these orbital energies in Hartree-Fock actually have a meaning of that in the sense that you can show that these eigenenergies in Hartree-Fock actually can be related within certain approximation to quasi-particle energies. And, you know, so in Hartree-Fock, obviously you have a different description of electron-electron interactions, but, you know, you could still say that the DFT exchange correlation potential somehow approximates the Hartree-Fock exchange potential, and therefore, you know, maybe it's not surprising that at least qualitatively there's some similarity.
Okay, that makes sense.
But yeah, if you didn't know anything, it should come as a surprise. Yeah. I agree with that.
Yeah. All right.
Okay, good question. All right, so band gaps. So they're often underestimated by DFT, and actually historically that surprised people a lot. So in the 80s, where, you know, people, you know, started to apply DFT to many different things, they were really surprised by the fact that DFT doesn't give you particularly good band gaps, and that led to a bit of a confusion for some time, but it's all resolved now. So that's what we'll talk about next. So we'll try to understand where this problem is coming from. So we want to understand what we need to do to get good band gaps. And to understand sort of the route for improving band gaps, we will go to Hartree-Fock. So one of the observations is that if we look at molecules, so not at solids, but molecules, Hartree-Fock often gives reasonable homolumo gaps. So homolumo gap is, of course, also is the analog of the band gap, right? It's the energy gap between occupied and unoccupied states. So let's take a look here. So here you see somebody has calculated. Okay, these aren't homolumo gaps. These are IPs. I think I couldn't find homolumo gaps, but what you can see here is, at least for the IPs, Hartree-Fock, which is basically these blue diamonds, they are you know, quite close to the diagonal here. So for molecules, Hartree-Fock actually gives you much better quasi-particle energies than, for example, PBE, which is in green. So you see PBE is much further from the diagonal than Hartree-Fock, and it's similar for the homolumo gaps, that Hartree-Fock actually gives you pretty good values for these homolumo gaps compared to, let's say, the LDA or the PBE. Okay, so that's sort of one hint, let's say, where we can, you know, what we need to do to improve, what type of theory we need to get good band gaps is basically this observation that Hartree-Fock works well for molecules. So let's talk for a minute about Hartree-Fock. So what do we need to do in Hartree-Fock? Basically, we have to replace the local exchange correlation potential of DFT. So local meaning that, you know, the exchange correlation potential is only a function of one position, right? So this is a local potential. So we have to replace the local exchange correlation. What am I doing here? With a non-local Fock potential. So we have this Fock potential, which is a non-local, so it depends on two positions, R and R prime, and it is given by this. So we sum over all the occupied orbitals, and we have something like this. That is the exact exchange or Fock potential. That's of course a much more complicated object than the local exchange correlation potential that we use in DFT. And if you ever try to run a Hartree-Fock calculation or a hybrid DFT calculation, you know that these calculations typically take much longer. And the reason is because we have to deal with a non-local operator here. And so the equation that we solve then is the following. So we've got our kinetic energy. We again got our interaction with the atomic nuclei. We got our Hartree potential. So these are all local objects. And then we have this Fock operator, which is a non-local operator. Right. So this is the equation that we solve in a Hartree-Fock calculation, and you see, so most of it is quite similar to the Cohen-Sham. In particular, this whole bit here is the same as in a Cohen-Sham calculation. It's only this little bit that is different. And so what I'll do is I'll write this one here in a sort of operator style, and in this way. And basically, what's often true actually is that the wave functions are quite similar. So the DFT wave function and the Hartree-Fock wave functions, they often look quite similar. And so if that is true, and it often is, so if psi Hartree-Fock is similar to psi DFT, then we can subtract the Cohen-Sham equation and the Hartree-Fock equation. We can subtract them from one another, and of course this bit here will cancel out, and what we'll end up with is basically a relation between the Hartree-Fock energies, which give you good agreement with experiment for molecular systems, and the DFT energies. Right. So and this equation makes a lot of sense. It looks basically like what you would do in a first order perturbation theory calculation. So you would basically correct the Cohen-Sham energies with the expectation value of the difference between the Fock operator and the exchange correlation potential. So that is shouldn't be very surprising. Okay, so Hartree-Fock works for molecules, but unfortunately it doesn't work so well for solids. So here I'm showing you the band gaps for a couple of different semiconductors and insulators. And Hartree-Fock are these red dots. And you can see that they are really, really far off. They're much further off than the LDA values that I showed you earlier. So, Hartree-Fock band gaps for solids are really a disaster. Okay, so that's another piece of the puzzle then. So Hartree-Fock works nicely for molecules, but fails completely for band gaps of materials. Okay, so a very natural question is then, you know, what's missing, right? I mean, so something must be different when I have a solid as compared to a molecule, and that something is, you know, missing in Hartree-Fock. And when we think about, you know, molecules and solids, obviously the difference is that in a molecule, typically there aren't that many electrons around, and in a solid there are lots of electrons, right? And somehow that must have cause the problem. And so typically when we discuss this problem, it's centered around the concept of screening. And we'll have to understand what that means. So basically, if I go back to my piece of material, so let's say again this is silicon or whatever, and I have 2 electrons in that material, and I want to study the interaction between these 2 electrons. Now, naturally, you would say, you know, each electron carries a charge. So let's say one is at R, the other one it's at a prime. So we'd say each electron carries a charge. So they repel each other with the Coulomb interaction. But this completely ignores the fact that there are many, many other electrons around. And these electrons, you know, also react to the presence of these 2 charges. So what's happening is that the presence of the first electron polarizes all the other electrons in the material, which we describe through a polarization density delta rho. And then this polarization density delta rho itself interacts with the second electron. And that typically makes interactions much weaker, because basically when I put an electron into a material, around that electron, the other electrons are repelled. So that means in the vicinity of that electron, there's sort of an excess of positive charge, and that makes sort of this potential of the electron weaker. And so Hartree-Fock actually only captures this direct interaction and completely misses the contribution of this polarization charge density delta rho. Okay, so what does that mean? So let's see. So the Coulomb interaction in a material is screened. And so if we look at the screen interaction between these 2 electrons, there is sort of the direct bit So that is just the bare Coulomb potential 1 over r minus r prime. But then there is the second contribution due to this polarization density. So delta rho, of course, depends on the position of the first electron. So we can express delta rho in perturbation theory basically in the following way, as in terms of the density response function chi times the Coulomb potential that is created by the first electron, right? So we put an electron here. This electron creates a potential, and then this potential results in a charge density delta rho, which when I use a linear response theory, I can calculate through the so-called density response function chi. And then the polarization density in turn creates a potential that the second electron experiences. So this is how screening works. And often we write this in a slightly different way. We write it basically as in terms of a dielectric function. So we say, so we have an interaction between the electrons that is reduced by a dielectric function. And of course, you know that the dielectric function in a material like silicon is something like 10. And so what that means is that two electrons, the interaction between two electrons is an order of magnitude weaker in silicon than if these two electrons would interact in free space. And that is something that Hartree-Fock doesn't capture, which is why it gives you this dramatic overestimation of the band gap in solids. Okay, so that is screening. There's one more thing about screening that's important, and that is that screening is energy dependent. All right, so what does that mean? So here in the picture that I've drawn, I've sort of assumed that the electrons are static, right? They're just sort of sitting there in a material, which is not very realistic. The electrons move around, and if they have a lot of energy, they move around very quickly. And if they have a low energy, a small energy, they move around very slowly. Now, if they move around very quickly, it might be hard for the other electrons to rearrange themselves, because the electron is maybe passing through the material so quickly that there isn't sufficient time for the other electrons to rearrange themselves. And in that case, you could say that this polarization charge density might vanish, because there's not enough time to establish that polarization density. While, of course, if I have a very slow electron, then I am in this picture where the electrons are almost static. There's a lot of time to build up this polarization density. And that's what it means that screening is energy dependent. Screening you would expect to be relatively weak for energetic electrons and much more significant for slow electrons or strongly bound electrons. Okay, so now we understand what Hartree-Fock is missing, and well, now basically it will be like a gender reveal party. I can reveal to you what this GW theory is that incorporates the aspects of GW, that incorporates the aspects of Hartree-Fock that work well for molecules, but fix the problem of Hartree-Fock for solids. So what you have to do, you have to replace the non-local Fock potential by another non-local quantity, but it's not only non-local, but also energy dependent. Potential that we call a self-energy. So it's a bit of a strange word, but you know, a self-energy is basically a type of exchange correlation potential that is non-local and energy dependent. So when we calculate GW energies, what we have to do, we have to basically, we can start again with our Kohn-Sham energies. And then instead of using the Fock self-energy, what we use here is, instead of using the Fock exchange potential, we use this GW self-energy in this correction term, right? So you see it's very similar to this correction term that we developed for Hartree-Fock, but now we're basically replacing the Fock exact exchange potential with this so-called self-energy. And you see the important difference is that the self-energy is energy dependent. And so you have basically, there is a need for a self-consistency, that the energy that goes into the self-energy must be the same as what you're calculating. Right, so that's clearly a more, again, it's more complicated than in Hartree-Fock theory. Okay, so we need the self-energy, and what is it? It has an exchange term similar to Hartree-Fock, but the crucial difference is that this exchange term is screened. And it has the slightly, so screened exchange spells sex, and it's given by the following. So again, we're summing over all the occupied states, like in Hartree-Fock, but now instead of the bare Coulomb interaction 1 over r minus r prime, we use this screened energy dependent interaction W, right? So this looks exactly like the Fock exchange term. The only difference is that instead of 1 over r minus r prime, I'm using the screen interaction W, which of course makes a big difference, as we discussed in the description of solids. But there is another term. So there's the screen exchange, and there's the other term that is the so-called Coulomb hole term. And I'll just give you a simplified expression. So it's not the most general one, but this is the one that makes the physics very obvious. So the Coulomb hole term is a local potential. So it has a delta function here. And what enters is the difference between the static screen interaction and the bare Coulomb interaction. Now, if you go back to what we know about screening, which is basically this equation down here, then you will see that the difference between W and V is this term here that involves this polarization charge density delta rho. Right, so this guy here is basically right? So this is a local potential. And what does it describe? It basically gives the potential at the position of the electron created by this polarization charge. So let me try to say that again. So you put an electron into a material, that electron polarizes its environment. So you get this polarization charge delta rho, and this polarization charge acts back on the electron, which created the polarization charge density. So that is the meaning of this Coulomb Hole term. So it describes the potential at the position of the electron caused by the induced charge density. Or pictorially, right? So you've got your material. You put an electron inside the material. You create this delta rho in the environment somehow through Coulomb interactions, and then the delta rho acts back on the electron, right? And that is the meaning, the physical content of this Coulomb Hole term. All right, so that is these two terms make up the GW self energy, so screen exchange and Coulomb Hole. And if we basically correct our Kohn-Sham energies, which, as I've told you, are unphysical, with this correction term, the hope is that you get good agreement with experiments. And I mean, you would be very surprised if that actually wouldn't happen after all that I've told you, but it works very nicely. So here you see the red dots are the GW corrected values of the LDA band gaps, and you see they lie very nicely on the screen diagonal. So so GW basically overcomes the band gap problem that you have in density functional theory. Okay.
Okay. Can I ask, how much is the computational overhead of using the GW approach?
Yeah, so it is significant.
Yeah, because of the self-consistent, I assume there should be like a nonlinear solver in there.
Yeah, so that actually is, I mean, you're worried about this point up here, and that's actually not the deal breaker. I mean,
really? Okay.
Because quite often you don't actually have to do the full nonlinear solver. Quite often, actually, you can do a Taylor series of the self energy around the Kohn-Sham, and that's enough. So very often the self energy as a function of energy is just a nice linear function, and so that part is often not quite so bad.
Okay.
There are cases where the self energy actually has singularities as a function of energy. Then of course, that becomes a bit of a problem. Yeah, so actually calculating the screen interaction is quite numerically intense. So that is sort of a very difficult quantity to calculate. And then of course you have the usual problem of dealing with a non-local potential. So there's a number of issues that you have to, there's a number of complications. But yeah, so we will talk about the steps and in the next lecture, and there's quite a number of steps that you have to go through in a GW calculation compared to a DFT calculation. So these calculations are usually not as automated as a DFT calculation. But that being said, I mean, some of these modern codes, a lot of have actually gone a long way in automating the process. So a lot of my students like FHI Ames, which also has a GW implementation, and it's actually, it's a lot of things just happen under the hood, and so it's actually not that much more complicated than running a DFT calculation. But yeah, I mean, in practicals, I mean, if you do a GW calculation for a system with 100 atoms, that is quite an achievement even nowadays. While a DFT calculation with 100 atoms is fairly standard, right? So just to give you a reference.
Yeah. Okay, thank you.
Sure. Okay, but I mean, GW is, it's not like it's only the band gap that GW gives you. It actually gives you a lot of things. So GW also describes, gives you lifetimes of electrons, right? So, if you put an electron into a material, it scatters with the other electrons, and that produces a lifetime of the electron. And that is something that you can calculate with GW. While in DFT, the Kohn-Sham, since the Kohn-Sham electrons are non-interacting electrons, they have an infinite lifetime. So, this is something that, DFT doesn't even give you qualitatively, this issue of electron lifetimes. And in GW, you can calculate it.
Okay. Can I ask a question about that?
Sure.
Is this due to the fact that the self-energy is non-emission?
Exactly. So it's the imaginary part of the self-energy. Yeah. So it has to do with that. Yeah.
So it's non-local, energy dependent, and also non-emission.
Exactly. Yeah. I didn't mention that additional complication, but yes, that's correct.
Right. Okay.
The other thing is that GW gives satellites, which is of course something that should be of interest to if you're a photoemission person, then you know that there's this photoemission process that I've shown you. So here I've introduced you to the simplest process in a photoemission experiment. Shoot in a photon, get out a photoelectron, and you create a hole. That is the simplest process, but there are actually more complicated processes. For example, when in addition to creating a hole, you create, for example, a plasmon in the material, and then the electron that comes out of the material has sort of less energy because some of its energy is used up in the creation of the so-called plasmon. And that gives rise to a secondary peak in the photoemission spectrum, which is often known as a satellite. And GW gives you those satellites, sometimes not very accurately in a quantitative way, but at least qualitatively, it gives you these satellites, which again, you cannot get from DFT. And finally, one thing I like about GW is that it's very physically transparent, right? I mean, I could basically tell you, what these terms mean, right? In the self-energy, it's quite, I can tell you what the physics behind these two terms is, but I probably couldn't really tell you what the physics behind the various terms in the exchange correlation potential of the local density approximation is, right? It's much more of a black box. you know, the exchange, the construction of exchange correlation potentials in DFT. So I think that that is also something that's quite nice and useful. Good. I think we're about an hour in, so why don't we take a couple of minutes, maybe until 10 past, to stretch our legs, grab some coffee, run to the loo or something, and then I'll try to make a start with telling you what a Green's function is. All right, guys, 10 past, we'll continue. So there were some questions. Let me just, what happened to the chat? So let's see. The psi r prime in the Hartree-Fock term should probably be evaluated at r. So did I mistype something? Okay, I'll have to double check that. And then the other question was, what's the limit of the lifetime that GW can calculate? Is that a question about how accurate it is? So, I guess what I can say about this question is that there are many factors that influence the experimentally measured lifetime. And GW is a theory of the electrons, right? So basically it captures interactions among the electrons that give rise to a lifetime. But of course, in the real world, there are other things that also contribute, most notably, for example, phonons, defects, surfaces. And that's, of course, not included in a standard GW calculation. So, you know, if you compare to experiment, you have to be quite careful. So that's sort of what I can say. Hope I did answer that question. All right, so let's continue then. And talk about basically how to derive GW, right? I mean, basically now I have kind of motivated it and told you what it is. The next thing I want to do is to basically tell you how you actually derive this theory from sort of very basic considerations. And so I'll try to give you an introduction to Green's function, which are sort of, it's a very powerful branch of electronic structure theory, but is almost sort of a separate community that does Green's function theory, and then sort of the DFT community. So these Green's functions are, for example, also used by people who do sort of model Hamiltonians. Okay, so what is it that we want to describe? And going again back to the very first slide, the second slide, what we want to describe are basically processes where we introduce extra electrons or holes into a material, right? So we said we start with the ground state, and then we introduce an electron or a hole into the material, and that then is relevant to photoemission spectroscopy, scanning tunneling spectroscopy, transport, and you know, many other things. So that. And quantum mechanically, this then connects us to this concept of a field operator. So these are quantum mechanical operators. So this is a creation operator, and without this little cross, which is known as a dagger, it's called a destruction operator. And these operators create or destroy electrons at position R and time t, right? So this is a quantum mechanical operator that describes sort of the creation or destruction of an electron at a specific location and a specific time. And the operator is time dependent, obviously, and this means we're using so-called Heisenberg picture of quantum mechanics, where the time dependence can be expressed in the following way. Right, so where H is, of course, the Hamiltonian that includes electron-electron interactions. Right, so this is this is the time dependence of any operator in the Heisenberg picture of quantum mechanics, right? So there's nothing special to the field operator here. It turns out that we can express the field operators in the following way. So psi of r can be written in terms of the cone-sham orbitals, and these operators, so these operators basically destroy an electron in the nth cone-sham state. And these other objects are just the cone-sham wave functions that you get out of your DFT calculation. All right, so let's check whether this is actually true, what I've told you. So as a test, we can do the following. So we can start with the vacuum. So vacuum means no electrons whatsoever. And then we act with this field operator onto the vacuum, right? So supposedly this creates an electron at position r, and then we want to look at this wave function at r prime, right? This is something that we could try to calculate. So what is this? So we can plug in what we know about the field operator and express it in terms of cone-sham orbitals. Because of this dagger, we have to take the complex conjugate of the wave function. And we've got an r prime Cn dagger vacuum, right? So, so this state here is a state where I have put one electron into the nth cone-sham orbital, right? And then I want to know what the wave function of that orbital is at r prime. So that is just psi n r prime. And now I know that because the cone-sham orbitals are a complete basis, if I do the sum, it gives me a delta function, right? And basically, this is, of course, what we expected, that if we create an electron at r and measure the wave function at r prime, this is 0 unless r is the same as r prime, right? So, so everything I've told you kind of makes sense. All right, so so these are these field operators which allow us, as I said, to create or destroy electrons, which of course is corresponds to these experimental processes that we probe in, for example, photoemission spectroscopy. So now we're in a position to introduce this concept of a Green's function. Sometimes also known as a propagator. And you'll see in a second why that makes a lot of sense, is because it describes the propagation of electrons or holes through the material. So let's first look at holes, because those are of relevance to photoemission. So in photoemission, we said that we start with the n electron ground state, right? Material before the photoemission experiment, it's in its ground state. And then we remove an electron or create a hole. So we use the field operator without the dagger. let's say we create it at position R and time t, and then at some time later, we can put the electron back in. And calculate the overlap with the ground state. So this is basically an object that tells us something about how the hole propagates from the time it's inserted into the material to the time it's removed from the material. And of course, what must be true is that T prime must be greater than T, right? Because we first must insert the hole before we can remove it. So this is a function that describes how a hole propagates through a material. And of course, we can write a very similar thing down for electrons. So for electrons, let's say we're doing tunneling spectroscopy, we can put the electron in, let it propagate in the material, and then remove it again. And this quantity gives us information about the propagation of electrons. And here, of course, T must be greater than P prime. Right. So I hope this makes sense, that these quantities that I've just written down tell us something about how electrons or holes propagate through a material, and that this in turn is closely related to what's measured in photoemission or scanning tunneling spectroscopy. Okay, so now we're in a position to finally write down what the Green's function is. It actually combines these two quantities in the following way. So there's a minus I, whatever, that's not really important. And then we've got these Heaviside step function, which basically express mathematically what I've written down here about the ordering of the times. There's a minus sign. Trying to make no mistakes here. RT. Right, so this is the definition of the Green's function, and depending on the ordering of T and T prime, it either describes the propagation of an electron through a material or the propagation of the hole through a material.
I think
now,
they use the dagger here.
Yeah, that should be a dagger. Yeah, sorry. I think that's hopefully correct. Yeah, thanks. Good. And because this is kind of a bit difficult to write, people often write it in the following way. They introduce what's known as a time ordering operator T. And not forget the dagger. Right, so they introduced this time ordering operator, which is just something that, you know, allows you to combine this long equation up here into the simpler one. And basically what it does, it reorders psi and psi dagger such that the one with the earlier time argument comes first, right? So that's what this time ordering operator does. But really, the important bit is this first term. But you'll quite often, you know, encounter it written in this way. All right, so this is the Green's function. And while I have sort of, motivated that, there's, propagation of electrons and holes through a material, yeah, okay, could be relevant. Now I want to make that connection to the experimental measurements. And we said at the beginning that what we really measure is a quasi-particle energy, right? Going back to the very beginning, what we said, what is measured is this quasi-particle energy, which was defined as the difference of the total ground state energy and the total energy of an excited state with one missing or one extra electron, right? That is what we figured out is being measured in these experiments. And what I want to show you next is that the Green's function, as we have defined it here, can be used to calculate these quasi-particle energies. Okay, and for simplicity, because we've talked about photoemission, I'll only focus on the term of the Green's function that describes the propagation of holes, because otherwise it's too much writing. So we'll focus on the whole part, which is theta t prime minus t right, so that describes the propagation of holes. Okay, so how can we learn something about basically the information that this Green's function carries? Now, one thing we can do is, of course, we can use what we know about the field operators. Basically, we know how to express their time dependence in this way. So that's what we'll plug in. So I'll just try to write it out. So we've got n0. Now I'm going to put in these exponentials everywhere. Psi hat dagger r prime e to the minus iht prime e to the iht psi dagger r e to the minus iht and 0. Okay, hopefully I did that correctly. Now here we have the case, and I guess I'll put little hats on all the Hamiltonian operators. Now, when the Hamiltonian acts on the ground state, like here or here, what we get is we can just replace the Hamiltonian by the ground state total energy, right? So this just gives us e to the I n0 t prime, and this just gives you e to the minus I e n0 t. Okay. So that's something we can do. So let's see, what do we have? So and then of course we can take this out of the expectation value. So what do we have now? So we've got the ground state, and then we remove an electron from the ground state at position r. Now the resulting state will of course not be an eigenstate of the system, but it will have, n-1 electrons. And so one thing we can do is we can insert here in this place a complete set of states, right? So we can write, we can insert a complete set of states of the system with n-1 electrons. And that's, of course, the same as inserting 1. Okay. And of course, when the Hamiltonian up here acts on this state, it again gives us the total energy of that state. So what we'll get here is basically e to the I e n-1 lambda t minus t prime. Okay. And then let's collect everything that we've got. We've got theta t prime minus t, e to the I, e n 0, t prime minus t, e to the minus n minus 1 lambda, t prime minus t, minus 1 lambda. Sorry, lots of writing. Psi hat dagger r prime, n minus 1 lambda, n minus 1 lambda psi hat r n 0. Right. Okay, that's what we get. And we can, you know, these expectation values are, of course, just functions of position. And so we call them, we can just give them these following names. So it's a little bit less writing. Okay. So we can, another important observation is that the Green's function doesn't depend on t and t prime separately. You can see it only depends on the difference, right? T prime minus t. So what we can do is we can then do a Fourier transform from time to frequency space. And what we get is then our final result, GRR prime, as a function of omega, right? So we transform from time to frequency space. And what we'll get is the following. We still have these wave functions here, n minus 1 lambda star r prime. And now because of this Heaviside step function, we get the following denominators. And then we have to also add a little infinitesimal to make the Fourier transform converge. But that's just a technicality. And now I'm adding back the electron term. And these are the denominators I'm getting in that case. Plus I. Okay, so this is what you get. And of course, the most important observation here is that these things in brackets are what we previously introduced as the quasi-particle energies. Which are precisely the quantities that are measured in a photoemission experiment. So this is the key piece, that the poles of the Green's functions are the quasi-particle energies measured in experiments. So while, you know, in DFT, there is no, you know, physical meaning to these Cohen-Sham energies, when we look at, when we find the poles of the Green's function, they have this very firm interpretation that the positions of the poles are, in fact, these total energy differences, which are known as the quasi-particle energies. Okay, and obviously in all of this, I haven't done a single approximation, right? Everything I've written down here is absolutely exact. Nothing's approximate.
Johannes, wait a minute. The second exponential, shouldn't that be, you know, inside the summation?
Oh, you're right. Yeah, I shouldn't take this out. That's right.
All right.
Yeah, that should go in here. That shouldn't, yeah, I shouldn't take this out. Yeah, it's a good point. Yeah, I guess, let's see. I mean, it doesn't matter. I guess I shouldn't, I guess I should have inserted my 1 maybe better here, right? And then I wouldn't have run into that problem.
Or between those two exponentials.
Or between.
Yeah, that's the same way.
Yeah.
Yeah.
Okay. Anyway, yeah. Okay, that's a good point. Thanks. Yeah, definitely should be inside the summation. That's correct. Okay, but final result is correct, I hope. Good. Okay. Actually, I should. I have the same typo. I have the same mistake in my notes. Better correct that right now. Okay. Perfect. So this is basically why these Green's functions are useful objects. Because they have this connection to the experimentally measured quasi-particle energies. But of course, at this point, we don't know how to calculate these things, right? Because what we would need to calculate is we would somehow need to know the exact energy of the ground state or the energy of the excited states with n-1 electrons. But where are we going to get those from? So at this point, everything is very formal, and not yet, there's not yet a recipe for actually calculating anything. Okay, so how do we get more useful expressions for the Green's function? And the first thing that we could think of doing is we could neglect electron-electron interactions, right? Of course, if there's no electron-electron interactions, I mean, it's trivial because there's no many-body problem. But it's still instructive to see what happens to the Green's function. Now, without electron-electron interactions, the states n0 and n plus minus 1 lambda are single Slater determinants, right? Well, of course, when there are interactions, we should think of them as linear superpositions of potentially many Slater determinants. Basically, these states here with an extra electron is in a particular Cohen-Sham orbital. So these n plus minus 1 states differ basically by the occupancy of one Cohen-Sham orbital. I guess I want to put an index n here. Right. And of course, in that case, we can express the difference between these total energies just in terms of these single particle energies. Right. So and similar, it turns out that we can express these wave functions that go into the numerator in terms of the wave functions of these Cohen-Sham wave functions. So let me show you how that works. So that was the definition, right, of these objects. And so this is how we defined them up here. Just repeating that definition. Now I can insert here what I know about this operator, right? We said that we can express this operator in terms of the Cohen-Sham orbitals in the following way, right? And then what we get is the following. And I should be careful. I'll make a little prime here because I have reserved the index n for the extra, the state where the extra electron sits in. It's a little bit subtle, right? So I'm just copying what I have. And I've got an n-1 lambda Cn dagger prime n0, right? And now what we said though is that the statement n-1 electrons has one electron missing in the cone-sham orbital n. And so only if n prime is equal to n will you get, only if you remove an electron from the ground state in that particular orbital will you get an overlap with the n-1 state. So in other words, so this gives 1 if n prime equals n and 0 otherwise. So in other words, what we get is that these complicated many-body wave functions just become the cone-sham orbitals when there are no electron-electron interactions. And then we get the following expressions for our non-interacting Green's function G0 in frequency space. We have basically the whole term, which is basically a sum over the occupied orbitals. And then an electron term, which is a sum over the unoccupied orbitals. And well, you can see that if you do a DFT calculation, and calculate the cone-sham energies and wave functions, then it's of course fairly straightforward to then construct the non-interacting Green's function G0. Let me also note that G0, we'll use that next week, is diagonal in the basis of cone-sham orbitals. Right. So if I look at this, if I project G0 into the spaces of cone-sham orbitals, what I get is just a Kronecker delta and then plus or minus this infinitesimal. So I think that's pretty obvious. Okay, any questions so far? Let me just see if there's anything, nothing in the chat. Okay.
I have a question. Where do you stop for the empty state? So the summation over occupied states, it's a finite number of terms, but the summation over empty states
is not. Yeah, I agree. Yeah, so I guess that's a fair question, and that is obviously where this, that is one of the issues why these GW calculations are hard to converge, because you have these empty state summations. So let's say you're interested in a particular frequency, omega, right? Then obviously, if the energy of a state is very far from the Fermi level, then that term will be quite small, right? So, if you want to calculate, if you're interested in the Green's function at a particular frequency, which is, let's say a frequency near the Fermi level, if you want to find the band gap, for example, then the correction that you get from empty states that are sort of very high in energy will be quite small. But at the same time, you can see that, this is a very slowly converging sum here, right?
Yeah.
So that is, that is one of the reasons why these empty state summations are, quite annoying in practical GW calculations. Yeah, so sometimes it's okay to use a few hundred empty states. Sometimes you need a few thousand empty states to converge. All right, so we know what we get when we don't have electron-electron interactions, but of course that's not what we're after. We want to know what we get when we do have electron-electron interactions, and so that is basically what we'll focus on next time. I'll just give a brief outlook on how to calculate the interacting Green's function. So let's see. So where do interactions come in? Where do these interactions come in? And when we look at this expression here, we see that we have these Hamiltonians, right? And these Hamiltonians can be written as a sum of two contributions. You know, one contribution that excludes the electron-electron interactions, and then, you know, the part of the Hamiltonian that captures the electron-electron interaction. So we can write H is H0, basically kinetic energy interaction with the nuclei, plus the interaction term, right? And so this contains these electron-electron interactions, which are the origins of all difficulties. All right, and now what seems maybe sort of from a physicist point of view, a natural thing to do is to do perturbation theory, right? So we have this Hamiltonian in these in this exponent. And you know, it seems quite natural to write it in the following way. You know, basically to use a Taylor series and you know, go on and on with it. Obviously, I have to do that for each of these terms here. So I'll, you know, I have several of these exponentials that I expand, and so what will happen is that this procedure generates a lot of terms. And you know, the bookkeeping becomes a bit of a problem. And so this is where this concept of a Feynman diagram comes in, which is basically a tool to help you keep track of these various terms. So what Richard Feynman basically proposed is to represent these contributions to the interacting Green's function in terms of diagrams, which in his honor we call Feynman diagrams. Okay, I guess we still have a couple of minutes, so I'll make a start with discussing these Feynman diagrams. So I will not, you know, I will not derive them. I will basically state the rules for these diagrams, and then next lecture we'll heavily use these diagrams. Okay, so what are these diagrams? So there's actually only three fundamental ingredients. So the one thing, of course, that we want to get is the interacting Green's function, right? Because that tells us the quasi-particle energies, and we'll draw this interacting Green's function as a double line that goes from position r in time t to position r prime and t prime, right? So that's the thing that we want to calculate. And the things that is easy to get is basically the non-interacting Green's function, right? So that we can construct quite easily, we said. And so we'll describe this one by a single line. And then, of course, the thing that is missing in the non-interacting Green's function is the Coulomb interaction, which is the third ingredient. Now, the Coulomb interaction, we think of an instantaneous interaction, right? So there's no time dependence, and indeed here the time dependence is just a delta function. So this is just a formal thing. It turns out that these diagrams, you know, if you have a different kind of interaction, then you can use the same diagrams. But for now, we're not considering a time-dependent interaction, and we'll describe this interaction by a wriggly spring-like line that connects the points RT and R prime T prime. And sort of the picture that you should have in mind is that, you know, the Coulomb interaction is mediated by photons, right? So what you should sort of think of is these electrons moving through the material and emitting photons and absorbing photons, or these photons generating electron hole pairs. So that's sort of the mental picture behind these rules. Okay, and the goal of this exercise is basically to express the quantity that we want in terms of the quantities that we have, which are these two, right? So we want to draw a bunch of pictures that relate these quantities, and okay, and basically what Feynman has come up with is a recipe for doing just that. So in step one of that recipe, you draw all topologically distinct connected diagrams, and I'll show you in a second what that means. With n interaction lines and 2n plus 1 G0 lines, right? So connected means that the diagram doesn't consist of two parts, right? So let's see. So this is the thing that we want, we said. So we want the interacting Green's function. And of course, if we don't have interactions, then the interacting Green's function is just the same as the non-interacting one, right? So this is basically n equals 0 case, right? So no interactions and one G0 line. Okay. All right. So this is the trivial stage. Now we'll come to the first order. So first order, we have one interaction line and three G0 lines because n equals 1. And at this point, there are two diagrams. So we start at RT. Then basically we emit a photon. We keep propagating. And then we reabsorb the photon. And we propagate to R prime T prime. Right? So that is a n equals 1 contribution because it has one interaction lines. And you see how we think about sort of the electron propagating and then emitting and absorbing photons. But there's another one that looks like this. So again, you propagate, then you emit a photon, and the photon basically creates an electron hole pair, which will denote by this sort of circle-shaped bubble. And then the electron continues to propagate to R prime T prime. So that's another n equals 1 process. So these are the first order processes. And now obviously we can go order by order. So let me now show you just the n equals 2 processes. So we again can start, we can emit a photon, then the photon, and we can propagate, the photon can emit an electron hole pair, which can recombine, create a photon, be reabsorbed by the first electron, and then the first electron continues to propagate. So that's one n equals 2 process, because we have now 2 interaction lines and 5 Green's function lines, 1, 2, 3, 4, 5. We can, and now there's actually many more at second order. So we can have something like this. We emit 1 photon, we propagate, we emit another photon. All right, so that's another n equals 2 process. We've got this process. What else? We've got the process where we emit one, and then we have this other type like this. We've got a process like this. We've got a process like this. We're still at second order, by the way, right? So all these have 2 interaction lines. There's a couple more. There's this guy. There is this guy. And finally, there's this guy. So these are all n equals 2. So you see how the number of diagrams, unfortunately, very quickly explodes as you go to higher and higher orders in perturbation theory. And so just to come back to what I just said, connected diagrams are the ones that, you know, consist of one piece. So none of these diagrams may consist of 2 separate pieces. And topologically distinct means that, you know, if you take one of these diagrams and deform it in some way, that doesn't make it a different diagram, right? So anyway, it's not terribly important. Okay, so I've basically shown you what these diagrams look like, and I think that's where we'll leave it. And then in the next lecture, I'll show you basically how to evaluate these diagrams and how we can use this or analyze this diagrammatic series, which then ultimately gives us this expression for the GW self energy that I've showed you about an hour ago. All right, are there any questions?
Yeah, I got one. Johannes, are these diagrams all equally weighted in terms of their importance? You've got a lot of diagrams. For example, if you just consider second order ones, are those, you know, equally weighted in terms of the importance?
Yeah, I guess you wouldn't. You probably. I mean, a priori, I don't think you would. Okay, so I guess it depends. I mean, we know that in certain situations, some of these diagrams are more important than others, right? And sort of people have over the years built up an intuition that, for example, let's say we're in the high density electron gas. There's a subset of these diagrams which is particularly important, and then similarly in the low density electron gas, there's another subset of diagrams that are particularly important. So they are not all equally important, but it depends on the system that you're trying to model, which ones are the important ones.
All right.
So yeah, so that's I think basically how we think about them.
Yeah. Okay. So I got another one, and if we just go back to the previous slides.
This one?
Yeah, this one. Yeah. How do you actually get the last equation? I mean, because G0 is a non-local object, and you just like sandwich it in between two states, and you know.
Oh, you mean what does this actually mean here?
Yeah.
So this means basically dr prime psi n star r G0 r prime omega psi n prime r prime, right? So that's what this means.
Okay, so they have the brackets have different R dependency. Okay, I got it. All right.
Yeah, fair question. Okay.
I have a question about the last part, about the diagrams and the green functions. So we shouldn't think about the electron at position R and T being the same of the electron of R prime T prime, right?
You mean because
when you say, you know, we let it propagate, it shouldn't be distinguishable, right?
Well, electrons are never.
So yeah, so what I mean is the electron that we find at R prime T prime, it can be a different electron from the one that's propagated.
Well, you can't say, can you? Right? They're indistinguishable.
You can't say, yeah, exactly.
So yeah, I mean, we don't know which. Yeah, it's one of.
What I'm saying is we can't label the electrons, say, you know, this one is propagating, right?
Right. I mean, yeah, I think, yeah, you're right. I mean, these are just pictures, right? I mean, be careful, and I feel like you're attaching a lot of reality to these pictures. Yeah, I mean, fundamentally, these lines represent Green's functions, not electrons, right?
Right. Okay.
Okay. Yeah, so I appreciate that we covered a lot of ground today, but hopefully it made some sense, and hopefully I'll see you all next week, where we'll, as I said, we'll try to sort of bring some, we'll try to use these diagrammatic expansions to construct a theory that then gives us the GW approach, and I think that is quite actually that'll be quite enjoyable, hopefully. All right, guys, thanks for attending and for all of your questions, and hopefully see you next week. Bye-bye.
Thank you.
Thank you. Bye.
Hey.